Welcome back. Today we're exploring multimodal transfer, how language models are extended to handle images, audio, video, and other modalities beyond text.
Multimodal models represent the next frontier in AI, moving beyond language only understanding to richer, more human like perception.
Let's start with the fundamental question, what makes a model multimodal?
A multimodal model can process and generate multiple types of data, text, images, audio, video within a unified framework.
For example, it might take an image as input and generate a text description, or take text and generate an image.
The key challenge is that different modalities have very different structure and representations.
Text is discrete tokens, images are continuous pixel grids, audio is waveforms or spectrograms.
How do you combine these into a model that can reason across them?
Let's discuss vision language models or VLMs which combine text and images.
VLMs have become very capable at tasks like image captioning, visual question answering, and image grounded dialogue.
Early influential VLMs include Clip from OpenAI, which learns joint embeddings of images and text.
CLIP was trained on hundreds of millions of image text pairs from the internet.
The model learns to map images and their captions to nearby points in a shared embedding space.
This enables zero shot image classification. You embed class names as text and find which is closest to the image embedding.
It also enables text to image search and image to text retrieval.
More recent VLMs like Flamingo, GPT-4V, Gemini, and Claude can engage in dialogue about images.
You can show them a photo and ask what's in this image or what should I cook with these ingredients.
How are these multimodal models architecturally constructed?
A common approach uses a vision encoder to process images and a language model to process text.
The vision encoder is typically a vision transformer or VIT or a convolutional network like ResNet or ConNext.
It converts the image into a sequence of feature vectors, essentially tokenizing the image into visual tokens.
These visual tokens are then fed into the language model alongside text tokens.
The language model processes the mixed sequence of visual and text tokens, allowing it to reason over both.
There's often an adapter or projection layer between the vision encoder and language model to align their representations.
This projection is a learnable transformation that maps vision features into the language model's input space.
Let's talk about training strategies for VLMs.
One approach is contrastive learning, like Clip uses.
You train the model to bring together embeddings of matching image text pairs while pushing apart non matching pairs.
The contrastive loss encourages aligned representations across modalities.
Another approach is generative training. The model learns to generate image captions given images.
This is an autoregressive objective. Predict the next text token given the image and previous text.
Flamingo uses this approach, interleaving images and text in training sequences.
Yet another approach is masked modeling. You might mask parts of the image or text and train the model to reconstruct them.
VLMs are often trained in stages. First, align the vision encoder and language model with contrastive or captioning objectives.
Then, fine tune end to end on diverse vision language tasks.
Sometimes the vision encoder is pre trained separately on image data, then frozen or fine tuned during multimodal training.
Similarly, the language model might start from a pre trained LLM checkpoint.
Let's discuss image tokenization more deeply.
Some models use patch embeddings, divide the image into patches, embed each patch as a token.
For example, a 202.4 by 224 image might be divided into 196 patches of 16 by 16 pixels each.
Other approaches use more sophisticated tokenization. DALI and similar models use discrete visual tokens from a VAE or variational autoencoder.
The VAE compresses the image into a latent code, which is quantized into discrete tokens from a learned codebook.
This allows treating images more like text as sequences of discrete tokens.
Now, what about generating images from text?
Text to image models like DALI, Stable Diffusion, and Midjourney have made huge strides.
These use diffusion models or autoregressive generation over visual tokens.
Diffusion models start with random noise and iteratively denoise it, guided by the text prompt to generate an image.
The text is encoded by a language model, and that encoding conditions the diffusion process.
These generative models are technically multimodal. They map from text to images.
Let's talk about audio language models.
Audio can be speech or non speech sounds, each with different processing needs.
For speech, the goal is often automatic speech recognition or ASR, converting speech to text.
Whisper from OpenAI is a powerful example. It's a transformer trained on vast amounts of multilingual and multitask speech data.
Whisper can transcribe speech in many languages, translate speech to English, and even detect language and timestamps.
It uses a spectrogram representation of audio, a time frequency visualization of the sound.
The model processes the spectrogram with an encoder, then an autoregressive decoder generates the text.
For text to speech or TTS, you go the opposite direction.
Modern TTS models can generate very natural sounding speech from text, sometimes conditioned on a speaker voice sample.
Let's discuss video understanding.
Video adds a temporal dimension to visual input.
Models need to process sequences of frames and understand motion and temporal relationships.
Some approaches sample frames from the video and treat them as a sequence of images.
Others use 3D convolutions or temporal transformers to directly model video.
Video language models can do tasks like video captioning, temporal action localization, or video question answering.
Now, what about cross modal retrieval?
This involves finding items in one modality based on a query in another.
For example, text to image retrieval finds images that match a text description.
Or audio to text retrieval finds text descriptions of sounds.
Models with aligned multimodal embeddings, like CLIP, enable this naturally.
You embed both modalities in the same space and use similarity search.
Let's talk about instruction tuning for multimodal models.
Just like text only LLMs, multimodal models benefit from instruction tuning.
You train on diverse vision language or audio language tasks framed as instructions.
Describe this image, answer the question about this picture. What objects are in this photo?
This teaches the model to follow multimodal instructions and be a helpful assistant.
Evaluation of multimodal models is more complex than text only models.
For image captioning, you use metrics like CIDR, BLAU, or Meteor that compare generated captions to references.
For visual question answering, you measure accuracy of answers.
For image generation, evaluation includes both automated metrics like FID and human evaluation of quality and prompt alignment.
FID is Fréchet inception distance, which measures similarity between generated and real image distributions.
There are also comprehensive multimodal benchmarks like VQF2, COCO captions, and MMMU.
Let's discuss challenges in multimodal learning.
First, data alignment. Paired multimodal data is harder to collect than unimodal data.
Second, modality imbalance. One modality might dominate learning, leading to underutilization of others.
Third, fusion strategies. How you combine information from different modalities matters.
Early fusion combines modalities at the input. Late fusion combines at the output. Middle fusion combines intermediate representations.
Fourth, computational cost. Processing images or video is much more expensive than text.
And fifth, evaluation complexity. It's harder to define and measure multimodal capabilities.
What about multimodal hallucination?
Just like text only models hallucinate facts, multimodal models can hallucinate visual details.
They might describe objects that aren't in the image or misidentify what they see.
This is particularly problematic in applications requiring high accuracy.
Grounding responses in visual features and training on accurate image text pairs helps.
Let's discuss future directions in multimodal AI.
There's interest in truly unified models that handle any combination of modalities seamlessly.
Models that can take images, audio, and text as input and generate any of these as output.
Also, models that understand 3D structure embodied in robotics applications.
And models that can reason over long videos, understanding narratives and complex temporal events.
Another direction is efficient multimodal models that work on edge devices.
Most current VLMs are large and resource intensive.
Finally, there's work on multimodal models that are more interpretable and trustworthy.
Understanding why a model generated a particular caption or made a particular visual decision.
So, to recap, multimodal models extend LLMs to vision, audio, and other modalities. They use encoders to map different modalities into shared or compatible spaces. Common architectures combine vision encoders with language models. Training uses contrastive, generative, or masked objectives. Applications include image captioning, VQA, text to image generation, and speech processing. And challenges include data alignment, modality fusion, and multimodal hallucination.
This concludes phase 3 on transfer architectures. We've covered what transfer architecture means, domain adaptation, PEF, zero shot and few shot learning, cross lingual transfer, distillation, RAG, and multimodal transfer.
Next episode, we're starting phase 4 on advanced architectures and innovations, beginning with mixture of experts.
Thanks for listening.
Until next time, keep learning and stay curious about AI.